So, all right, so let me first start by talking about the problem that we're trying to solve. So let's say that we have an application, like a banking application, for example, and it has some data that it stores in a database. Now it's going to want to modify or query this data, so it's going to execute some transactions. And it's not going to execute these transactions itself directly on the database representation. It's going to issue these transactions to a database management system, or DBMS. And it's the DBMS that's responsible for updating the underlying database representation and returning to the client application the results of any queries. Now, from the client application perspective, we'd really like that this DBMS is correctly implemented, because if it behaves incorrectly, that means that our application may behave incorrectly. However, in practice, this DBMS may be a black box system, maybe it's proprietary. And so the question is, in a scenario like this, how can we tell if the DBMS is running correctly? So if we think about it, actually, from the client point of view, we don't care that the DBMS is really implemented correctly. We just want it to run our transactions correctly. So in the paper, we define this notion of observational correctness, and I will just give you some intuition for this here. So we assume that we have a set of client-logged observations. These include things like the initial database state, the starting and end times of transactions, the transactions themselves, and the results of any queries. And then observational correctness of the DBMS is then the property that says, does there exist a correct execution of the transactions in this log that is consistent with the observations recorded by the client? If we have this, then we know that the DBMS implementation that gave rise to this log is indistinguishable from a correct one on these transactions. So this is what we want to check. There's currently no way of checking this, or there wasn't, so we decided to come up with a way of doing this. In doing this, we had to contend with some challenges. So the first one that I'll mention is that DBMSs provide different isolation levels, and these govern the extent to which transactions can see the effects of other executing transactions. So for example, one isolation level is serializability. One way of formulating this is that if we have a serializable isolation level, we expect that there exists some order of the transactions such that each transaction reads only from the most recent database state. On the other hand, we can also have a different isolation level, like read committed, in which case the transaction can read from potentially any past database states, and even reads from the same transaction may read from different states. So these are two different isolation levels. In practice, there are more. We'd like to come up with a way of checking observational correctness that is flexible enough to accommodate different isolation levels. The second, somewhat related challenge is that if we look at the language used to write transactions, the operations and statements of this language are usually such that their behavior is defined with respect to a particular database state that the transaction can read from. We just saw that transactions can read from potentially many database states, so we can't directly use semantics that's like this. And the final challenge is that of scalability. Scaling becomes harder as we have isolation levels that allow for more and more non-determinism in which states can be read from. And also this becomes challenging as we have higher numbers of transactions and higher complexity of transactions. So I'll talk about each of these. I'm going to start by talking about the second one. So the way that we deal with this is we take our original semantics that is only allowing their transactions to read from a single database state, and we just lift it to a version-aware semantics that allows the transaction to read from sets, any of a set of database states. So the idea for the version-aware semantics is basically that it lets us, as I mentioned, execute transactions with respect to a set of potentially readable states. So we can take an example of maybe we have this transaction that's trying to deposit $100 into the bank account with ID 2. As an example, and if we run this transaction with respect to like the set of two states, then the version-aware semantics will allow us to read from either of them. So this is a non-deterministic semantics. Our version-aware semantics also produces the set of writes performed by the transaction, the result of the final query that you would find in the transaction. In this case, there's nothing, and also read records, which keep track of which states were read from for each read. Now, if we run the transaction according to the version-aware semantics with respect to a set of states di, this is going to take us to a new set of database states di plus 1. And this is just all of the states in di, but with one additional state, which is the result of applying all the rights of this transaction to the latest state in di. So with the version-aware semantics, we can actually check observational semantic correctness. So this isn't full observational correctness. We don't have anything about isolation levels here. But in terms of the semantics of the transactions, we can check something. So the way this works is we can take our initial state from our log, and from this construct our initial set of database states, and then run all the transactions in the log. And then we can use the results in the execution of the semantics. We can use the queries, the query results there, and the query results in the log to construct a set of observational semantic correctness constraints. And if these are satisfied, then we know that the DBMS implementation is observationally correct with respect to this log. If we don't have that they're satisfied, then we don't know. Why? Because, well, remember the semantics is non-deterministic, so there could be a different run of the semantics that does have these constraints satisfied. So what we really want to do is find whether there exists an execution of this semantics that satisfies these constraints. And I'll come back to this later, because first I'd like to talk about the missing ingredient for checking observational correctness. So, which is basically, we've talked about semantics, but what about the isolation level? So we need to make sure that all of the states that were read by the transaction are actually something that is allowed by the isolation level. So the way he handled this is we formulate the conformance to a particular isolation level I as a constraint ci, and this is parameterized over a set of database states, writes, and read records produced by the semantics. And we have that if the constraint is satisfied, then the execution that produced the database states, writes, and read records was correct. And the nice thing about handling isolation levels like this is that it's easy to define new isolation constraints independently of the semantics. So if we have many different isolation levels, as mentioned earlier, then we can just define some new isolation constraints, and this is independent of how the semantic part is handled. So if we put all of this together, we can start with a log of observations and execute the transactions in the log according to the version-aware semantics. We can use the results of this execution and the recorded query results in the log to formulate semantic correctness constraints. And we can also use these results to formulate these isolation correctness constraints. And if we have that all of the constraints are satisfied, then we know that the DBMS implementation is observationally correct with respect to this log. So the thing is, this is really only looking at a single run of the semantics. It's non-deterministic. We want to see if there exists any execution of this semantics that satisfies these constraints. So one way that we can search for this execution is that we can just encode this entire thing symbolically and give it to an SMT solver. And if the SMT solver says that it's satisfiable, it finds such an execution, then we know that the log is observationally correct. That the DBMS is observationally correct with respect to the log. And otherwise, if it says unsat, we know that it's not observationally correct. There's no execution that is going to give us what we saw in the log. So the question now is, how do we do this encoding? So something we could do is maybe like a bounded model checking style encoding, right? The thing is that this kind of naive encoding scales really, really poorly. So instead, what we do is we define a new semantics. This is a partially symbolic semantics. So what it does is it works over and directly generates partially symbolic representations of sets of database states, reads, like query results, writes, and read records. And it also generates constraints on the transaction's execution that need to hold for it to have successfully executed. We can then use these directly to formulate semantic correctness and isolation correctness constraints as SMT formulas, and just conjoin these and give them to the SMT solver. And the rest of it's pretty much works the same way. So I don't think I'll have time to really talk about what's going on in the partially symbolic semantics, but to give you some idea here, this basically is going to work like symbolic execution when it has to, but it will try to, when possible, execute the semantics concretely as much if it can, and also maintain as many values concretely as possible. And by doing this, we can greatly reduce the complexity of the formulas that we end up giving to the SMT solver. So in terms of actual experiments, when we ran some experiments with the naive encoding that I mentioned before, this sort of BMC style encoding versus the constraints we get with this partially symbolic semantics, where the naive encoding gave us formulas that took the SMT solver around 40 minutes to solve, the partially symbolic semantics generated constraints were able to be solved in under 2 seconds. So that was one way that we deal with scalability. Another way that we deal with scalability is by developing a bunch of heuristics. Most of these are helpful. One of them is only helpful for workloads with high non-determinism. I don't think I will have time to talk about them now, so please read the paper. If you have more questions about this later, I'm happy to answer them. So we implemented all of the ideas that I presented so far in a tool called Troubadour, which can be used to audit client-side DBMS logs. Troubadour supports a fragment of MySQL, and depending on the isolation level and the complexity of the transactions, it can scale to handle hundreds to thousands of transactions in 5 minutes. And we applied Troubadour to an industrial DBMS under development. It was able to check a log of around 1 million banking application transactions in under 2 hours, and a log of 66,000 transactions from the TPCC online transaction processing benchmark in a little over 89 hours. And in applying Troubadour to this system, we were also able to discover 2 previously unknown bugs in the query processor, which was useful and also pretty cool. So I'd like to, at this point, touch really briefly on some future directions that we're currently working on. So one is that we would like to eliminate the need to provide any kind of initial state or a set of initial states to enable an angelic verification. And the other thing that we'd like to do is eliminate the need to provide any of this timing information about the transactions. Troubadour already supports some ability to explore different orderings of these transactions, but it's not complete, and we'd like to explore better ways of doing this. So that's pretty much all I have to say about this. If there are any questions, I'm ready to take them. Thank you for listening.
So this looks very exciting. I was wondering if you had any thoughts on whether the same technique could be applied. I'm really hard to hear with the mask on, aren't I? I was wondering if you had any thoughts as to whether the same technique could be applied to conditions like opacity or persistence or the sort of distributed system style consistency that we are working on in other domains.
So I haven't really thought about that too much yet. I do think that a lot of the machinery here can be used to check other kinds of properties. What we were looking at for a little bit was like equivalence of refactorings of transactional workloads under weaker isolation levels, and I think this might be useful there. I haven't thought about what you mentioned specifically, but I could see a lot of this being useful for checking other kinds of things as well.
A quick follow-up. Do you know if the workloads that you are currently able to verify could be verified by the opacity checker community under the opacity conditions, as opposed to, which is just a different kind of transaction condition?
I don't exactly know. So it depends on how I'm not sure how directly applicable this is because of how the isolation constraints are defined. So if it's something that can be defined in this way, then maybe, but I'm not sure. Yeah.
Unfortunately, I think we run out of time for more questions, but let's thank the speaker again and get the next one plugged in.